oral exam of Anand Ashok, who came here from Delft after doing his undergraduate and master's degree at Delft University of Technology, and in 2008, I think, and has been working on a number of different topics, including evaluating the accuracy of hot wire anemometry under various conditions, and looking at spatial and temporal response of those probes in order to make some measurements in these turbulent wakes. Now, in Delft, the defense of a thesis is a very formal affair where I would be wearing a morning coat
and an academic gown,
and with the academic gown on top of that. So it's a choice, actually. And it is a highly ritualized event. We don't do that. Obviously, I'm not dressed for that occasion at all, but you are. So with that, take it away.
Thanks, Lex, for the introduction. Thanks, everyone, for being here. So I'd like to present to you today some measurements that I've taken over the past couple of years on the wake of an idealized submarine model that performs sort of static pitch and yaw motions. As this audience will be well aware, turbulent wakes are really ubiquitous in nature and engineering, and there's a real need to understand how these wakes might evolve in all three dimensions and also temporally. Why would we like to study such submarine-like wakes? Well, we obviously have an interest in reducing drag, potentially increasing maneuverability, perhaps reducing noise. Some of these objectives can be met if we are able to reduce the footprint of the wake that is shed by this body. Now, in order to be able to reduce that, we actually have to be able to characterize and study the wake as it occurs in real life, which is, of course, at high Reynolds number. So for a fully submerged vehicle, which is the configuration that I'm going to be studying today, the similarity parameter that we will look at is the Reynolds number. And so submarines, of course, encounter very high Reynolds numbers due to their speed and their scale. And there's a real need to understand and to extend the Reynolds number range that these bodies have been studied at. And that will be the subject of the latter part of today's talk. It's of course difficult to do full-scale tests, and so what we can do is we can use a pressurized wind tunnel, which we have at Forrestal campus, that allows us to achieve Reynolds numbers about an order of magnitude higher than is achievable in conventional facilities. And I'll come back to that in a little bit. So just to give you kind of a global overview of the complexity of the flow that might occur over a submarine that in general might perform maneuvers in different axes and so on. So we see here a body vortex. This is the most dominant feature of the flow that we will focus on today. So that body vortex occurs when the boundary layer encounters a pressure gradient over a pitched or yawed body. And in response to that pressure gradient, it rolls up and curls up into these vortices that I will discuss in more detail later. This is just an illustrative drawing for now. Of course, we have a sail that's required for navigation purposes and also for guidance and control of these vehicles. The fact that we have the sail results in junction or so-called necklace vortices that occur at the junction between the sail and the body. In the aft part of the body, we see the presence of fins, and there's a propeller also. There's a sail tip vortex associated, of course, with the sail. So there's a great deal of complexity in this flow. And as I said, we will focus today mainly on the body vortex. I mentioned to you that submarines are large. This is just to give you an idea. This is Her Majesty's ship, the Astute, 97 meters long, 11 meters in diameter. The two gentlemen here that are standing on top of the sail are probably the equivalent of a 4-story building above the surface of the ocean. So these are beasts, large vehicles. Just to recap, I will focus on the body vortices. Of course, we won't be looking at a sail, but we will need a support because we would like to study this body either in water facilities or in wind tunnels where we need to be able to place the body in such facilities, and we use a support. That support will mimic the sail in that it has the same geometry as the sail. And relative to the flow, it's semi-infinite. However, the sail tip vortex that I mentioned previously will be missing. We will not characterize that aspect of it since we look at a semi-infinite body. Pitching motions are, and yawing motions are shown here. They are rotations about the y and z axis, respectively, and as I said, we will restrict ourselves to the bare hull and we won't look at appendages. Just to make that a little clearer, this is the axisymmetric flow configuration where the flow vector is coincident with the axis of symmetry of the body. This is the support. We're looking at the configuration inside view here. If we continue looking at it inside view and there's an angle formed between that axis and the flow, we call that angle pitch, the pitch angle alpha p, that will come up in the talk. And this is then the yaw configuration, which distinguishes itself from pitch. How? Well, this is a body of revolution. As you might imagine, a body of revolution that's pitching or yawing might be the same, but the fact that we have that support introduces the change between pitch and yaw. So any differences that we see between pitching and yawing motions can be attributed to the support. So there's just a few conventions so we're all on the same page. A few words about what the literature, what scientists already know about submarine-like wakes. So here is a snapshot taken from Aiden et al. This is a RANS computation. You see here vorticity contours shown in the wake of the sail. So there's a complex interaction between these necklace vortices that I was talking about earlier and the hull boundary layer that grows over the body and ultimately interacts with the fins also. They did not look at the wake. This was done by my predecessor Juan Jimenez, who covered an unprecedented range of Reynolds numbers. This is among the highest Reynolds numbers available in the literature today, so ranging from 1 to 67 million. And what he found was that the mean velocity in the wake collapses well when scaled appropriately in similarity coordinates on the side away from the sail, but on the support side, he can clearly see the effect of those necklace vortices in the sense that the velocity profiles did not collapse for the range of Reynolds numbers and downstream locations that he studied. Now, this is the mean velocity profile. The streamwise Reynolds stress did not collapse at all over the range of downstream locations that he looked at. So self-similarity was not reached. And so this might be a clue for us that these wakes have rather long development lengths, which make them also rather difficult to study. So this is what we know about axisymmetric wakes. Of course, that was just a very brief overview. Axisymmetric wakes have been studied in great detail over several decades. We focus on the static pitched configuration in this study, so a few words about that. This is a simulation by Gross et al. So here you see vorticity and skin friction contours shown. His main purpose here in this study was to look at the Reynolds number effect, and he found that there was a qualitative change in the topology going from a closed separation bubble type separation to what's known as an open separation that occurs. He did not trip the flow, and therefore he did not see secondary vortices, which are characteristic of this flow at high angles of incidence. This was captured using very detailed lasered upriver velocimetry measurements taken by Wetzel et al., where you can see the footprint of the primary vortex and also a tiny secondary vortex. Why is that secondary vortex important? It influences greatly the trajectory of the first, and therefore you miss the flow physics if you don't simulate the secondary flow. Now, Carlson et al. Did simulations of this experiment, and they managed to show this difference very clearly. So here in their simulations, they show that for the untripped case, you don't see the footprint of that secondary vortex, whereas you do for the tripped case. I'm mentioning this because these wakes are rather sensitive to tripping, and this is a theme that will be recurring during the talk.
What turbulence model was he using? It was a one simulation, and shouldn't be any transition model, implicitly assumed in the runs in the modeling.
Model, but I think it's the K epsilon model, but I don't exactly remember now. Gross et al. So in these studies, symmetry was assumed. Now this is a key point. So half the flow was computed in these two studies, and half the flow was measured in this study. Fu et al., who, it's interesting to note, Matt Fu, who now works for Marcus Halpmark, that's his father who did this work, so this is an experimental fluid mechanics family here. And they noticed that they didn't assume symmetry. So here, this is an early particle image velocimetry work where they look at the instantaneous flow structure, and they in fact find that instantaneously the wake on a body that's nominally symmetric can actually be asymmetric. And that's an important point, because we will find that rather than even in the instantaneous flow, we will find it even in the mean flow, as I will show in a moment. So this brings me now to the objectives of the current study. We've had a number of investigations looking at axisymmetric flows, axisymmetric wakes. We've had works that study the body vortex and how that shed over the body itself. But relatively few works are focused on the wake itself, which is of course what the Navy is really interested in trying to understand the dynamics of the wake in order to ultimately be able to reduce its footprint. So that is the subject of today's talk. We will look at the wake structure of a static idealized submarine model. We'll investigate differences in mean and instantaneous flow structure for pitching and yawing motions. We will investigate the sensitivity of the pitched wake to disturbances. As I've already alluded to, these wakes are known to be sensitive to disturbances, so we'll investigate that. And then finally, we will take a look at the Reynolds number dependence of this pitched wake. We will extend the range of Reynolds numbers that have been measured towards more realistic measurements. So quick roadmap for the talk. I will start off with some very simple dye flow visualizations performed in a water channel. These are simply meant to illustrate some of the salient flow features that characterize this flow. Then we will transition to the sensitivity study. Then I will show a gallery of quantitative flow visualizations, if you will, of the wake and pitch and yaw. And then we will look at the high Reynolds number measurements. At the risk of sort of infantilizing this audience, this Reynolds number-ometer will show up every now and again during the talk, just to give you an idea of where we are. So the dye flow visualization will weigh in at about 40,000. The low-speed wind tunnel experiments, which will form the bulk of the results, are about 2.4 million, and then the high Reynolds number range extends that a little bit. Of course, we know that there are a couple of faculty members in this department who have a certain preference for certain parts of this ometer, and that is, of course, well known. So the flow visualization then, as promised. So I'll play this animation in a moment, but let me just describe to you quickly what might be going on. So here is the body. We see the flow goes from top to bottom. This is a top view of the body. This is the nose. We have channels in this body which are connected to small orifices that I've drilled in the nose. These orifices will inject some dye into the flow, which we can control using mass flow controllers, and that will allow us to give a very qualitative sense of what this flow looks like. So this is performed with fluorescein and rhodamine dyes. So what you see here is pretty classic. This has been seen by many authors. There's an azimuthal pressure gradient, a favorable azimuthal pressure gradient over the nose. This causes fluid elements to be lifted up from the windward side into the leeward side. They then get wrapped up into these conical vortices that are then discharged into the wake. That was a pitch angle of 15 degrees. Now let's look at the same in yaw. I mentioned to you previously that all differences between pitch and yaw can be attributed to the support. So keep that in mind here. This is now the side view, not the top view. The flow goes from left to right. We see a strong coherent vortex at the top. We see the sail here and a weak diffuse vortex that's shed due to the interaction of that separating boundary layer with the support. So we see a rather different pattern in pitch as compared to yaw. If we zoom in on that a little bit more clearly, we can see here, this is done with colors, just color dyes. We can see here the separation region occurring. This is of course at low Reynolds number, keep in mind. In the wake of this support, we can see that quite clearly here. I'll also be talking about the windward and the leeward side. So the windward side is where the fluid comes from initially, and then the leeward side is where it's shed. So that's the side that we're looking at. So that was just a few illustrations of what we might expect in terms of flow features in this flow. We of course want to extend this now to slightly more representative Reynolds numbers because submarines don't swim at 0.1 meter per second. How do we do that? We resort to a wind tunnel. So here we can have a free stream velocity of 40 meters per second that allows us to get to a Reynolds number of 2.4 million. Here is a schematic of the experimental setup. Some initial experiments were performed, using point measurements using a hot wire traverse. But the bulk of today's data will come from stereoscopic particle image velocimetry. That's quite a mouthful, but for some of you that's well known. For those that isn't, it's a technique that involves seeding the flow with tracer particles. These tracer particles are then illuminated using a light sheet. In this case, that light sheet is in the cross plane, because that's the plane in which we're going to see the footprint of those vortices that we saw in the flow visualization movies. And then we're going to image these with 2 cameras in stereoscopic configuration, which allows us to resolve all 3 components of the velocity at a single plane. And we'll do this for multiple planes. So let's jump straight into a visualization of these results. So what do we see here? We see a scaled model of the submarine. The flow is from left to right. The submarine is pitched, in this case at an angle of 8 degrees. The free stream velocity is 40 meters per second, the Reynolds number 2.4 million, as I mentioned. We look at contours of the streamwise velocity, suitably non-dimensionalized, and we look at the wake evolution moving from 2 to 26 diameters downstream of the trailing edge of the model. We see the pattern of 2 vortices that I mentioned before, which is expected. However, perhaps what is less expected as we move from 2 to 8 diameters is we immediately see that there seems to be an asymmetry in this flow structure. Notice this is now time, this is a time average flow structure, not instantaneous, this is time average. And we see that there is, even in the time average case, there is an asymmetry between these. Let's zoom into that a little bit. This is for the 3rd downstream location measured. We indeed see primary vortices of unequal strength. There's about a 25% difference in strength, so quite a considerable difference. This is separation occurring over a symmetric body, and we get asymmetric vortices. Unexpected result. These asymmetric vortices are potentially undesirable. Why? Because they might cause rolling moments and side forces to occur on the submarine, which we might want to mitigate. So we need to investigate this a little further. I've changed the color bar here on you a little bit to be able to see this footprint a little more clearly. This is the baseline case, so basically the same picture that I showed before. On the left is the same picture. On the right, contours of mean vorticity now shown. This is the nominally pitched wake. Now, I alluded to the fact that this wake is sensitive to disturbances. What kind of disturbances can we throw at this wake, and can we then see what it might be sensitive to? Tripping of the flow is clearly an issue, so we're going to visit that. Free stream turbulence can be a point that we're going to look at. Surface roughness can be an issue. These are experiments. Models can only be machined to a certain degree of accuracy, and of course in real life fouling of these structures will occur in the ocean. And finally, we can exaggerate model positioning. I've claimed here that this model is at 8 degrees of pitch, but for all you know, this model could be slightly yawed, could be slightly rolled, and so let's look at the effect of that. Let's start with the effect of the tripwire thickness. This is the untripped case. This is a tripwire of 0.8 millimeters, double again. We look at contours of the streamwise velocity again, and these by the way, are point measurements. This is one of the few images that I will take from the point measurement campaign. We see an asymmetric wake structure. This is at x over d of 8, and we can see that qualitatively there's no real change in the pitched structure. Now I won't show this, but in the case of yaw, there is, and for all the results that I will show for the rest of the talk, we will choose the 1.6 millimeter tripwire. Why trip the flow at all? Well, in real life, the boundary layer would transition from laminar to turbulent. In a lab, that may not happen as reliably as we want. So we put the tripwire so that we can distribute the vorticity in the boundary layer over the entire leeward section of the flow. And we can reliably generate a boundary layer that transitions from laminar to turbulent, and we are looking at a turbulent wake, which is what we want to study. If we then go back to the baseline case, now let's look at the effect of free stream turbulence. So one, it's a little bit like going to the optician, you know? Is A better or B? So the effect of free stream turbulence, how is this created? This is done using a coarse grid, a square mesh with a solidity of 23%. The grid turbulence causes a free stream turbulence of 3%. Naturally occurring is about 0.3 in the tunnel. So we up the free stream turbulence by an order of magnitude, and we see a relatively modest change in the flow structure for the pitch case. So let's now look at surface roughness. So these are adhesively backed bumps. So maybe some barnacles are growing on this submarine. The bump height is about 1.6 millimeters. That's the same as the thickness of the tripwire. This is inside view. Notice that there's the support. It's the airfoil shaped support. So we put these bumps on the submarine at different azimuthal and axial locations. So I'll play this little animation that will take us through the different perturbations that we've put on. So notice here that I've also, the degree, if you will, of asymmetry has also been shown. So 1.3, so about 30% difference in the circulation strength was the baseline case. And when we, let's play that again, when we include the surface roughness, there seems to be, relatively speaking, modest changes. These numbers are, I would class this as changes to within experimental error. So surface roughness seems to have a relatively modest influence also on the actual wake structure. What about exaggerating this imperfect model positioning that I was talking about? Let's start with yaw. What is the effect of small yaw angles on the pitched wake? We are back again to our familiar baseline case. Let's now add a yaw angle of -1. So moving from the baseline case to a yaw angle of -1, we see that finally we see a change. But this change is essentially just to rotate the wake slightly from the baseline case to the case that we see now. The asymmetry still remains, and you can also see that a little bit in the time average contours. If we exaggerate that a little further, this is now more, I would say, than a small perturbation to the flow, yaw angle of 2 degrees. We see that even though the contour suggests that the strength is similar, we can see that this wake is rather different from the baseline case. So what this effect of this wake is doing is essentially rotating this wake from left to right. We can see that a little more clearly if I show you also the cases, the symmetry cases 1 and 2 degrees. So the point that I'm trying to make here is that the effect of yaw angle can change the position, the rotation of the wake, but doesn't fundamentally, in my opinion, change the wake structure and the preference that the wake seems to have to separate on one side slightly differently from the other. Let's look at the effect of roll. So we're pitching it, we're looking at small yaw angles, now we're going to roll. So if we look at roll, so this was the baseline case, the roll case has a very subtle influence as you might expect. It simply translates the wake to the left and to the right, depending on the roll angle that you look at. So that concludes the brief sensitivity study that we have performed on the wake. It seems to suggest that free stream turbulence, surface roughness, and tripwire thickness don't result in qualitative changes in the pitched wake structure. Small yaw and roll angles move the wake around, but don't fundamentally change that asymmetry that we see. So if we now look at galleries of quantitative flow visualizations of this wake, so I start now with the axisymmetric case. Juan studied this wake, so we won't focus on this too much, but important to notice that the top of this wake is axisymmetric as we might expect. The support removes that axisymmetry, and we can also see the support wake evolving downstream. So alpha P of 4 degrees, this is a similar plot to the one that I showed previously. At 4 degrees, the separation seems to be incipient. It's not exactly, the vortex structure isn't exactly clear, but that asymmetry that I was talking about certainly persists. I've shown this plot already, but now perhaps we understand that this asymmetry is rather robust to different disturbances that we have put into the flow. Moving from 8 to 12, we notice something a little interesting. The velocity deficit at 12 degrees is actually smaller than at, is actually smaller than at 8 degrees, and this has got to do with the fact that as we increase the angle of incidence, the separation will move forward along the body, and so the wake has actually evolved a little further, and so the velocity deficit has had a chance to recover, which is why we see a lower velocity deficit, even though, as I will show later, the circulation strength of the vortices will increase with pitch angle. Oh, and it's very important to note the limitation of the experiment as well. So look at the last 4 downstream locations here. The vortices that are shed at this angle are actually impinging with the boundary layer of the wind tunnel itself. And so this is kind of the limitation of the experiment. We can't really go beyond this pitch angle. So let's zoom into that. So here we look at the wake at 2 diameters downstream. We see this jet of velocity that is being forced between the 2 vortices. These are again those contours of streamwise velocity, vorticity rather, that I showed. This convinces you a little bit more of that asymmetry. So clearly there's a precession of those vortices about one another. The vorticity is diffusing rather quickly. And by the time we get to the final downstream location that we look at, that vorticity is diffused into the wake, and to the sensitivity of the measurement that we have, we are not really able to pick it up anymore. So let's contrast that now to the yaw studies, where we expect the influence of the support to be rather dominant. This is yaw of 4 degrees. We immediately see that this is a rather different pattern to pitch. So what's happening here? Well, in pitch, the separation was happening on the left and the right of the body. In yaw, it will happen on the bottom and top. Of course, we've seen in the previous diflow visualization that the separation from the bottom was affected by the support, and that's shown here. It's interesting to note that by the time you get to the final downstream location, you only seem to see a footprint of a single vortex. What's going on here? Well, if we increase the angle from 4 to 8, we can see that a little more clearly. We see the footprint of a weaker vortex and a stronger one. The influence of the support, as I said, is dominant here. We see the support wake, and we see that the asymmetry is such between the strength of the 2 vortices that the strong vortex essentially rotates, pulls the weaker vortex and annihilates it by the time we get to the final location. So if we zoom into that as well, similar to how we did in pitch, we see here the large strong vortex, and this is the probably unsteady, though we don't know that for sure, weaker vortex, causing a strong rotation in the flow. That vortex footprint persists. This is different, slightly different to pitch. Even at the final downstream location, the footprint of that vortex is very strong and remains because it convected downstream relatively undisturbed relative to the pitch case. So this is an important distinction between pitch and yaw. So if we try to estimate now the circulation, these graphs show the absolute value of the non-dimensional circulation. CW and CCW refer to clockwise and counterclockwise vortices. The clockwise vortices are consistently stronger, 10 to 15% stronger. That's responsible for that asymmetry, for that precession that we saw in pitch. Of course, we expect that the net circulation will remain constant because this is a wake where there's no further generation of vorticity in the wake itself. In yaw, we see that the stronger vortex is much, much stronger than the weaker one, which can only be tracked for a few downstream locations before it is essentially into the noise level of the measurement. Now, all of this information that I've showed you so far is time averaged. We're looking at the average structure, velocity structure. Now let's look at it instantaneously. So perhaps it's not so clear, but I've plotted these little deviations, so-called error bars. They represent one standard deviation of the circulation, the instantaneous circulation from the mean. So in order to show you that, I'll show animations in a moment, but essentially what this refers to is the fact that this is a pretty steady wake. The instantaneous deviations from the mean circulation are on the order of 15%. So no large changes there. And you can see that a little bit more clearly here. On the left is the time average picture that we've seen before, on the right rather. On the left, I show you an animation of different ensembles that are taken. Note that this is not time resolved. At 40 meters per second, that's not possible with the currently existing infrastructure. And so we see that the foci of the vortices move in a relatively tight locus of points, not deviating that far from the mean time averaged case. And this is true not only in pitch, but also in yaw, where we can see that this wake is remarkably steady. This is, of course, all at a Reynolds number of 2.4 million experiments performed in a low-speed wind tunnel. I mentioned before that we would like to extend the measurements from Reynolds numbers that are achievable typically in the lab on the order of 1 million or so to slightly higher. 1 order higher, if possible. So I will now present some measurements that we've taken in the high Reynolds number test facility. This is, again, a low-speed wind tunnel, but in this case, it's a pressurized facility. How does this help us? This high pressure causes high density at constant volume. And we take advantage of the fact that air has a weak pressure dependence on the dynamic viscosity. This means that by pressurizing the air, we effectively reduce the kinematic viscosity of air, which allows us to generate these high Reynolds numbers at essentially constant free stream velocity. We would like to ask the question, is there an effect of Reynolds number on the wake topology and evolution that I've shown in the previous slides? This experiment, as you'll see in a moment, is technically rather challenging. We will consider only 1 pitch angle and look at it over 6 Reynolds numbers. This is the facility. It's out at Forest Hill campus. These pipe sections are standardized oil and gas pipe sections. These bolts are about slightly larger than my head. One section takes about 10 man-hours to assemble or disassemble. So there are some pretty challenging technical requirements that need to be met in order to be able to take data in such a facility. I won't bore you with those engineering details, though I'm very proud of them. But I will show you an animation of the experiment. So here you see in the foreground the submarine model that's pitched at an angle of 8 degrees. You see the traverse here in the background, which I inherited. It's a real marvel of engineering. I inherited most of that traverse from a predecessor, Juan Jimenez. And this allows us to place the probe in a radial, azimuthal, and different streamwise positions. I mentioned to you before that the previous data was taken with optical techniques. Of course, we would need optical access for that. This is a hermetically sealed pipe. There's no optical access. So we rely on traditional methods, hot wire anemometry and point measurement techniques, to be able to study this wake. So we will only be able to look at the mean and statistical quantities in this structure. We won't be able to look at instantaneous behavior. So if I play this little animation, the traverse, this is all controlled by a LabVIEW program outside of the wind tunnel. The traverse is now zeroing itself. Of course, I know where the wake is because I performed these experiments before in the low-speed wind tunnel. So I tell the computer where to put the probe, and off it puts the probe in that location, takes data, and moves on its merry way. And this is how we take the data. We'd like to take a couple of components of the velocity field. So we do that using a so-called crosswire probe, which requires a directional calibration to occur, and this also can be performed using this traverse. And finally, in all of the images that I've showed to you before, we want to look at a wake evolution. And so this is done not by moving the submarine, but by moving the traverse that holds the probe, a rather large streamwise motor, a lead screw, some cabling, 1 or 2 cables that are needed to be able to power the motors and to take the data that we need. So with that, after about a year of engineering, it's finally time for a little bit of fluid mechanics. So we look at the wake evolution starting at a Reynolds number of 0.1 million. This is at alpha p of 8 degrees. The data that I show is plotted in a way that's similar to the data we've seen before. These are contours, again, of the mean streamwise velocity. The free stream velocity is 5.5 meters per second. And we do this is an atmospheric test case, if you will. This is just at 1 atmosphere to see if we can indeed take data like this. Due to the limitation of the size of the test section, we can only look at the wake up to 14 diameters downstream of the stern of the model. The flow, of course, is from left to right here. We notice at this Reynolds number that there is a thicker support wake that sort of merges with the separated vortices that are shed on top of the body. This was a test to see if we can take data in this way. The experimentalists in the audience will be a little worried here because I'm showing the 2.4 million case again. And as every good experimentalist knows, you never take data more than once in any case. So I've done that here, and so this matches the Reynolds number achieved in the previous low-speed wind tunnel experiment. How have I achieved that? Keeping the free stream velocity approximately constant, pumping up the pressure from 1 atmosphere to 16 atmospheres, and this allows us to achieve that same Reynolds number. So we see the wake structure here. By this time, it's sort of familiar. we see those two vortices as they evolve downstream. It seems there's a hint of asymmetry, but we don't quite see that as clearly as in the low-speed wind tunnel case. Or do we? Well, I showed you, this slide was a comparison of the streamwise contours. I flashed through that a little bit too quickly. This is results I've shown previously. This is the new data. Let's now look at the z component of the velocity instead. That's what that directional calibration was useful for that I showed in that previous movie. So we see the z contour. I told you that the vortices force a strong jet of velocity between them. Well, that jet of velocity in blue is clearly angled in this case. And also the contours here are not symmetric. If we look at that face-on, we can clearly see that this wake is also asymmetric. So now, in two different facilities, in two different facilities and over two different models, at the same Reynolds number, we see an asymmetric wake. Of course, I've already showed to you before that free stream turbulence, surface roughness, and imperfect model positioning are not the primary factors that drive this asymmetry, so keep that in mind. So if we transition then from 2.4 million to 4.8, because I wanted to extend this, right? So again, the free stream velocity is almost constant. We pump it up, we double the pressure to 32 atmospheres. We see here that that asymmetry now is persistent, but the wake structure has not really changed. Moving from 4.8 to 9.6, same story. The wake structure looks about the same. That asymmetry persists. Up to 19 million, this is now a pressure of 128 atmospheres. So now we get ready for the most difficult case, which took me quite a while to take. Doesn't look too impressive, but believe me, it is. The pressure in the wind tunnel is 200 times atmospheric pressure. I bumped up the free stream velocity a little bit from 5 to 7 meters per second. You'll see the measurement matrix is a little bit smaller than in the previous cases. That's because during the run, there are large-scale temperature increases that occur, which means that we have a much shorter period, window of time in which to take data before I end up blowing the seal and, giving headaches to a lot of people. So I have to put the points where it matters here. So we still managed to look at the wake structure, and clearly now we can say that Reynolds number independence has been achieved. Note that the Reynolds number here isn't a specific value. It's sort of a range, if you will. So I nominally set the tunnel to about 28 million at the start of the run. By the end of the run, it's about 30 million due to that temperature increase, which further increases the pressure, further increases the density, which further lowers the kinematic viscosity, which increases the run. So I mentioned Reynolds number independence. So if we look at the minimum velocity at the vortex core, it becomes Reynolds number independent beyond about 4.8 million. So we can see the 2.4 million case here, deviating considerably. The other cases seem to agree. The same for the peak turbulence intensity, the peak streamwise turbulence intensity that seems to collapse rather well also. And so we suggest that this wake is Reynolds number independent as long as the Reynolds number based on the length is larger than 4.8 million. We hope that we have made our computational colleagues a little bit happy with this piece of news, because it means that expensive computations of this wake above this Reynolds number, we suggest, are no longer required. With that, I would like to conclude the talk. For all the Reynolds numbers that I've measured, I observe an asymmetric vortex wake structure in both pitch and yaw at small angles of incidence. We believe this to be a novel result. The tripwire, free stream turbulence, and surface roughness have had a negligible influence on the wake structure in pitch. Small yaw and roll angles do translate and rotate the wake, but they are not responsible for the asymmetry that we see. We observe a remarkably steady wake in both pitch and in yaw, and we suggest that the pitched wake is Reynolds number independent above 4.8 million. By way of future work, I would like to see in the future some experiments that perform PIV at a much lower Reynolds number to confirm whether we can ever get this wake to be, this pitched wake to be symmetric. Some boundary layer suction at some important locations along the body would be of interest to see if we can reduce the extent of the wake. The Navy would be very interested in the effect of the sail tip vortex, particularly at high Reynolds number. And then my esteemed colleague is going to perform what I think will be one of the greatest experiments that our lab has ever performed, And that will be a levitation of the same submarine model that I showed to you, magnetically levitating this model, removing the need for the support, and taking the same wake measurement data that I took without the support, and to compare the two data sets together. I think we will make the Navy very happy with that. So good luck to Leo. And finally, I would like to acknowledge my lab. It's been an honor to work with you, Lex. Thanks for the support and encouragement these years. Sean and Marcus, very important mentors to me. I'd like to thank them for helping me to grow up a little bit as an experimentalist. And I've worked with some really great and talented lab mates here who have made my time very enjoyable. I'd like to thank the department. You know, experimental work is not possible without great technical support. So thanks to Glenn, Mike, John, and Dan for helping me to rise to the technical challenges of this research. This faculty, of course, are known for their great teaching and research. In particular, I'd like to thank Gigi and Eddie for being my readers, and for Miko for his continual advice and encouragement during my PhD. It never hurts to thank the people that paid for this, the Office of Naval Research. And with that, I'd like to take some questions. Thank you.
So the floor is open for questions. We'll take questions from the audience first, and then
I'm going to miss something right at the beginning. Was the asymmetry always on one side of it?
Yeah.
So why the left and not the right?
That's a good question. So both in the, you would have noticed that both in the low-speed wind tunnel and in the high Reynolds number facility, the submarine has a preference to rotate clockwise. Not entirely sure why that's the case. Obviously, differences in separation location is what's causing this asymmetric pattern. But why that was chosen to be on the opposite side, I'm not sure. In the surface roughness simulation, little animation that I showed, that's exactly what I was trying to do when I put surface roughness on sort of opposite side. I was sort of willing the flow to separate earlier on one side rather than the other. But that didn't quite pan out. So
why don't you put the support on the opposite side?
To take measurements on a submarine that's upside down.
Yeah.
This would be possible, but given that the separation occurs on the leeward side of the body in any case.
No, I mean, you have two halves of your submarine, right?
Sorry?
If they're not symmetric about this plane, right? And you have the support here. If you put the support on the other side, flip it over, right? You should get the same bias, if your argument is correct.
Yeah. I think we probably will.
I'm talking about model asymmetry, right? That could cause to bias the flow in one direction or in the other.
It's possible. I mean, it's an awful large coincidence. I mean, I inherited the model that I showed the low-speed wind tunnel experiments from Juan. That was, I think, machined by Bill Dix. And the model that I have was machined here in the lab. So, I mean, it would be a huge coincidence if we suddenly started to see different patterns just because the submarine is upside down. But clearly, that's something we could try. Tyler.
I was going to follow up on that too. Do you think it's possible that it's because of surface irregularity? Because there's a total runout inherent to the cylindricity of what you have machined.
So that's what the surface roughness perturbation study that I did attempted to address.
Right.
So
there's
surface
a difference
roughness
between surface roughness and surface irregularity, right? If the submarine is slightly elliptical, or there's a twist in ellipticity because every lathe turns the same direction when it's being made, for example, there could be something tripping because there's a shape irregularity in your part.
It's possible. I think that the disturbances that I subjected this wake to are much stronger in magnitude than what you suggest, and the wake wasn't sensitive to those. So I'm not sure that it would be sensitive to what you suggest.
But those were a little bit further behind, right? The tripping was way in front, so it would seem that these disturbances that palettes were after the transition of the wake. My other question: did you try to trip one side of the submarine?
No, this was not tried. We tried the untripped case. What is your thinking behind that? So this would allow one side.
I mean, if your suggestion that it's the way, the place where there's a slight difference in the transition location. That is that what I understood?
No, difference in separation location.
Separation.
Separation
Sorry.
location.
Okay.
Yeah. Yeah. Which could result from differences in transition location too, but I believe that this tripwire was sufficient to trip the boundary layer to turbulence. So the wake is a reliably turbulent wake in all cases.
I have another question, right? I think you know, we chatted about that before, but if you can put your you know, your more extreme case on the
pitch
medium Reynolds number, yeah, in which you have the wake, and I just wanted to, yeah, that one. If you want to comment a little bit about wind tunnel interference.
So the blockage of
Yeah,
this,
the interference between, you know, the vortex that is shed and the walls of the wind tunnel. Not
So-
as much as the blockage.
okay, so I think what Gigi is referring to here is that this is basically a wake that's in ground effect, right? So as this wake evolves, it starts to come closer and closer to the wall. So it's well known that you can model this from a potential flow point of view with mirror vortices that exist below the surface of the tunnel. So this was a little, very simple, almost trivial simulation that I did for myself to see how close do the vortices need to get to the surface of the tunnel before I need to start worrying about these vortices being affected by the wall. And so you need about 2 to 3 vortex cores. You need to come closer than 2 to 3 vortex cores in order to really see an influence of that wall. And that doesn't occur, that only starts to occur starting at around x over d is 11. So the ground effect kind of range, if you will, starts to occur in that range. Does that answer your question?
Yeah.
There is, of course, the interaction with the boundary layer, which would not be captured by the
Right.
fault calculation.
That's true. That's true. Yeah, that's true. Yeah. So in terms of circulation trends and things like that, I can't really consider
No,
these
no.
downstream locations at all.
What if you look at the flow without a model in there? Do you see any sort of twist to that? It's a strictly linear.
Yes, pretty much. But I mean, obviously, there's free stream
I mean,
turbulence, which is
your
relatively.
perturbation isn't very big, and the only thing I can think of is that in accelerating the gas, you must be using.
So my lab mate Tristan actually suggested this to me. So these are both closed return wind tunnels, right?
But
So
how
you
is
have
the
a
flow
front-
accelerated? It's got a propeller that's going around in one direction,
That's right.
and probably
But
the
they're-
same in the low and the high speed.
They're
one?
different.
They're different.
They're different.
Okay.
So in the low speed wind tunnel here, you would have expected the flow to come around, and so it would come to the left on the left side.
Yeah.
And HRTF is the exact.
Okay.
So 2 different models, 2 different facilities.
You might want to mention the observations on missile aerodynamics.
Yeah. So one thing here, of course, is that these were performed at relatively modest angles, right, as compared to some of the things that I showed in the literature. So at very high angles of attack in the 1960s, people were very interested in missile aerodynamics. So these are slightly different bodies to the types of bodies we see. They're basically like delta wings. They have sharp noses at very high angles of attack, above 40. And there you see this asymmetry is a well-accepted way of controlling more than living with it. You control the flow with that because your rudders and your control surfaces, they don't get clean separated flow. So they're not very helpful to you when you're an F-16 pilot at 45 degrees angle of attack. And so what you actually can do is you can use the asymmetric bursting of these vortices, basically it's vortex bursting that's occurring, as a way to control your actual flow. There have been workers that have suggested this. But at low angles with blunt noses. So what I do is low angles, blunt noses. What they do is sharp noses, high angles. So what this asymmetry that we see, this is as far as I know, not observed for blunt bodies at low angles.
Right.
That's the claim.
So that's the difference, because that's you have vortex bursting, right, at a high angle of attack.
So that was an open question when we increased
Yeah,
the
no, I
number,
understand.
whether we might see vortex bursting or not. But that's
So I have another question, is that, so apart from a structural point of view, from a fluid point of view, would you recommend to stay with this, circular cross-sectional shape, as a result of your study, or actually modify the, the hull shape somehow to be more elliptical or more?
That's an interesting point.
I understand the structural point of view that, the payoff probably is making a round submarine for pressure reason, right? But suppose that you don't have pressure reason. You don't have to worry about it.
Yeah. So if instead you had an elliptically shaped,
Yeah.
how would that look?
Do you ever feel that it would solve some of the issue about
Probably make that more
symmetry,
difficult.
make things a little bit more control?
I think the best thing that you can do to this wake right now, the most obvious thing, is just remove the sail. So the Navy is very stubborn because the captain needs to stand on top of the sail when he comes to the harbor. So if you can just remove this ego aspect of it, get rid of the sail, that's probably the first thing I would do. But in terms of the actual shape, so in other words, if we would have an ellipsoid,
A shark shape, right? So more squeezed.
yeah. I'm not entirely sure what that would do to the strength of the separation.
I'm not concerned about the strength. I'm concerned about if you have a feel on reducing this asymmetry.
Oh, okay. Yeah, that's probably likely, right? Because that means that if the separation can occur more on a flattened surface as opposed to something which has a lot of curvature, then that pressure gradient that we're talking about, if we can make that azimuthal pressure gradient more gradual around the shape, if that's what you're referring to, then it might help to stabilize the two vortices, but it's already quite blunt, actually. I mean, it's enough to, this nose cone is enough for, to store the sonar systems and so on.
They spent about probably 6 years arguing these things on the old America's Cup, boat. Well, they had, this is a bulb, right? Whether they had round with a Stratford ramp in the back, or whether you have, kind of squeeze and sharp like.
This is for the ballast?
Yeah, for the ballast.
Yeah.
So it's not, it's an open question, right?
When you were telling me about this about maybe a year ago, you were viewing this asymmetry as an annoyance. You maybe were not expecting it. And the thesis, you were kind of neutral about it. And now it seems that now you've progressed to the point where you're saying this is a finding. So are you now confident that this is, you've done it.
I think that's exactly right.
Thinking about it.
Thank you for that comment, because that's sort of the evolution of a graduate student almost.
You have to make it a finding at the end.
Yeah. No, initially, yeah. I mean, the first thing I remember the first measurements we took with this was using point measurements. So that's something I neglected to mention. So these asymmetries we see, it's not a function of the measurement equipment. So even with point measurements, we see that in this tunnel here. So when I saw that first, of course, the first thing I thought was, this is wrong. I spent a year working on this experiment, it's completely wrong. You can never get an asymmetric structure from a symmetric body. That's not possible. Then Lex pointed me to these very high angle sharp nose body studies. And that got me thinking that it might not be something that's necessarily unphysical. And then now that I've done it in 2 different facilities with 2 different models, and I've tried to really perturb this wake in different ways, it seems it might be a fact of life, that there is a preference in one direction rather than the other. And so this does have implications for rolling moments. It does have implications for how the how the wake evolves downstream and in terms of control. So yeah, I think I am more confident that this is a real finding now. I think that's right.
Okay, I just have one question. Came back to the slide where you have the different size tripwires. There's something interesting that struck me. And so if you look at the two vortices, the stronger one's relatively robust to the different size tripwires, but the weaker one does have some variation. Any reason for that, or comment, or is it just a computational matching things?
I wouldn't consider this to be I would consider this to be within experimental error.
Okay.
So I certainly don't think we can draw any conclusions from this. What is, I will say, something which I wanted to include in the talk, but decided not to in the end, was, this might be a little fun to see. So more color pictures. So untripped case, D is 0.8 millimeters, D is 1.6. I haven't done 3.2. So Juan had this at this tripwire. This is the model I inherited. So this is the first measurement I took. So this is yaw of 8 and yaw of -8. So the first thing you see, you don't get mirror symmetry in your flow. So this was another thing that told me something wrong. And Gigi was the one who pointed out that it might have to do with tripping. So the first thing I did was I took the tripwire off. We looked at the untripped case. That gives you more or less mirror symmetry. And then you double the tripwire thickness, and you get something that, again, to within experimental error, is symmetric, which is why we decided to go with the 1.6 millimeter case for all the data that I've shown. So the flow is sensitive to the tripwire, just not in pitch.
So what do you think? What do you expect the results will look like when you remove the strut, the support strut? How will that change?
So if I move it forwards or backwards?
No, when the levitation.
Oh, the levitation.
Yeah. What?
So I think that the asymmetry is not going to go away. I think we're still going to see that. Obviously, the yaw case and the pitch case are going to be will then be the same motions. But it will be interesting to see whether the asymmetry that we see from the left-right separation is of equal strength to the top-bottom separation. So, and this would then maybe point more to Tyler's point, where there is the parts of the body have more curvature than other parts, and so then it becomes very sensitive to different local curvatures, let's say. Yeah. And so that would be something interesting to look at. The other thing as well is that a previous group, what they did was they weren't interested in the wake. They were looking at surface flow patterns. So they had the body mounted on a sting, and then they took measurements where they put the support on the side, and then they removed the support and took the same measurements again. And what they found was that the separation on the clean side, on the leeward side of the body, was unaffected in pitch to the support as long as the angle was not above 15 degrees. Above that, there started to be an influence of the support, even in the pitch case, because implicitly in the study that I've discussed today, I've basically told you that I basically assumed that the support doesn't have a role in pitch and only has a role in yaw. That whole thinking was based on this previous study in Virginia Tech by Roger Simpson's group that have done this. So we could do our own, where we could see, we could see that for ourselves, particularly at high Reynolds number, because they weren't able to do that at high Reynolds number. So I think the asymmetries will be there. Pitch and yaw will be the same, but it'll be interesting to see if they yield exactly 90 degrees mirror symmetry between the two.
Any other questions? Then we'll thank Anand, and we'll ask the audience, faculty members and research staff, to remain behind. Thank you, Anand.